The nonlinear p-center problem on a tree network and duality. So last time we actually started a discussion of duality in rudimentary form. I tried to give you some insight on duality. Essentially, let me just remind you of what we were doing. We were investigating the beta Bij values from top down, from largest to smallest. And as soon as we identified the Bij value, which is next to be entered, we entered an edge whose one node is I, the other node is J. And these edges, okay. These edges, when you start entering them one at a time, they start forming a certain graph. And in that graph, if P equals, for example, 3, at the time your first 4 clique is formed. A clique is a complete graph consisting of 4 nodes. So when P equals 3, you looked for a 4 clique, which is formed the first time in this order. And that actually suggested that if you were doing the same thing on a graph with n nodes, with every edge present, except that you were looking for a 4 clique, which you found in the ordered way of entering these edges, then essentially that's equivalent to, well, actually not essentially, but it's equivalent to finding a 4 clique whose smallest arc is largest. So it's a maxi-min problem. You're trying to maximize the minimum arc weight of the clique you're looking for. What's the clique size? Well, if you're dealing with the p-center problem, your clique size is p plus 1. Okay? So that's an interesting relationship. And there's an intuitive way of seeing that, using that procedure. Now we're going to somehow formalize it in a more general context, the nonlinear p-center problem context. You've actually seen the nonlinear one-center problem before. I talked about it. It looked kind of complicated. Nevertheless, it was really not too complicated in my judgment. So in this case, again, we have nonlinear monotonically increasing loss functions, fj. I take the domain to be 0 delta j, where delta j is the farthest distance you can go away from Vj on the tree network. And the domain, the range is, because of the monotonicity, it's going to be this one. The smallest value you get for fj and the largest value you get for fj. Delta j, by definition, is the maximum distance from Vj, x in the tree. And fj is some sort of a monotonic function. This is fj of 0. And if that's delta j, this is your fj delta j. Okay. In addition, nonlinearity is not enough to complicate the problem, so we make it even more complicated by imposing upper bounds uj on the distances. So this is an upper bound on the distance of Vj to a nearest center. And our eventual interest is to minimize the maximum loss when we place p-centers and subject to additional constraints on the distance of every vertex vj to a closest element or closest center. Okay. Let's just make some assumptions here for convention. The first assumption I make is the upper bound is less than or equal to the farthest you can go away from delta j. Of course, that's reasonable because if uj is greater than delta j, then that upper bound is not really effective because the farthest you can go away from vj is delta j anyways. Okay? So any bound greater than that is meaningless. It's redundant. Yeah. Right, but just let's just make it equality because, as I said, if uj is actually greater than delta j, you just replace it with delta j, in which case this is satisfied. Okay. Number two, an indexing convention. If I of ui is less than or equal to fj of uj. Well, ui is in the domain of definition of fi, likewise, of course, uj. So these are well defined, and we just assume this is to be the case for I less than j. So the p-center problem, this is supposed to be a small p. Okay, p-center problem is, well, I just need this for proving stuff, that's all. It's just the indexing convention. You can always re-index the facility vertices so that this convention is satisfied. No problem with that. Okay. Okay, so in the p-center problem, again, we're trying to find a minimum radius rp, except that my notes have this as zp. Is that okay if I change it to zp? Otherwise, I may just make a mistake later on. So let's just change it to zp. Minimize a variable z subject to fj of dx vj is less than or equal to z. For every index j, all right, so the first one is something familiar to you from the single facility case when p equals 1. In that case, instead of capital D, we had small d. Small d x vj, the distance of small x to vj. So we evaluate the loss function fj at that particular distance value, and whatever outputs, that's the loss. That loss should be less or equal z, and this should be true for even the maximum loss, the greatest one. Okay, z is greater or equal to every one of the losses. And in this case, of course, you are interested in the closest distance value from vj to a closest element of the set x. Whatever that distance is, you evaluate your loss function at that value, and you want your z to be the maximum loss, so you're minimizing the maximum loss. Okay? Z is greater or equal to each of the losses, including the maximum. Okay. Now, the upper bound, uj is just a constant, Of course, such upper bounds need not be present for all vertices, but for some vertices it could be present. If an upper bound is not present for a particular vertex, you simply take it to be delta j. Otherwise, it's smaller than delta j, and that is your distance constraint.
And that usually is a variable or parameter like R over Wi.
You can think of it that way, but this is just a constant, whereas in the R over Wi case, R was a variable. So I wouldn't make that analogy.
It's a
Okay.
predetermined constant.
Yes. It's part of the input data. Yes. Yeah. It's stated here. It's a given number. Now, first of all, this problem, regardless of what you're trying to minimize, may or may not admit a feasible solution. If your upper bounds are such that having, where's my other constraint? I forgot this. Yeah. There's this constraint also. Sorry about that. When you restrict your number of points to p, and you have upper bounds present, your upper bounds may be such that p points may not be able to actually cover everybody within the upper bound. Okay? So, this zp could be infinite in that case, if there's no feasible solution. Plus infinity. It's not unbounded. It's whenever you have infeasible problem, in that case you have no finite value for the p radius. Can it be minus infinity at all? Can it be minus infinity under any circumstances? No. If there are feasible solutions, then this z will be the greater or equal to the losses, and this is always greater or equal fj of 0, right? Because the distance is greater or equal to 0, and this is a monotonic function.
Should we also include non-negative monotone function?
Well, no, we don't have. Well, let's see.
Because we always assume that it's non-negative.
Well, let's just not make that assumption for now. Fj of 0 is just a finite number. It's a lower bound on this. And so z is always bounded. Z is bounded below by each fj0. And of course, it's bounded below by the maximum of fj0s. And for that reason, z cannot be minus infinity. That's the point. But if you make this negative, it may cause additional difficulties later. So we'll see that, okay? So let me define a new function now, Ej. Ej evaluated at z is the inverse function fj evaluated at the minimum of Z itself and Fj of Uj. Okay. Now, if Z is less than Fj0, in that case, Z is too small, so it's not in the domain of definition of Fj inverse. It will be the smaller of these two, okay? In that case, of course, this would not be well-defined. So this requirement, I just impose it to make it well-defined. Now, when Z is greater or equal to Fj0, it could be too large, but in that case, you will take Fj of Uj to be the minimum here, in which case Ej of Z is still well-defined. Remember, Fj inverse has domain defined by Fj0, Fj delta J, and range 0 delta J. Okay? So that the argument here defined by the minimum of two numbers is always in the domain, as long as Z is greater or equal to Fj0. Okay. There's a reason why I did that, because I want to be able to deal with the problem in a more meaningful way. And with that definition, the original problem is equivalent to the following. Minimize Z subject to dx Vj less or equal Ej of Z. So this problem differs from the old problem in two ways. First of all, dx Vj Uj constraint is replaced by something new, which somehow takes care of the first one as well. Number two, we appended the constraint Z greater or equal alpha, which is not present here. Okay? Despite that, the two problems are equivalent. Why? Well, of course, the reason is you can rewrite this in the following form. If what is satisfied? If Z is in the domain of definition of Fj inverse, which means Z should be greater or equal Fj of 0, less than or equal fj of delta j. If z satisfies this, then you can apply the inverse function to both sides and you have that. Of course, if that is not satisfied, the equivalence, this will not hold, okay? Well, when z is between fj of 0 and fj of delta j, there are two possibilities. Well, actually, when z is, just a second, yeah, there are two possibilities. Z is either less than or equal to uj, or it could be also greater than uj, okay? So this is the case where z is less than or equal to uj.
Less than or equal to UJ or FJ
uj. fj of uj. Ah, okay. Yeah, fj of uj. fj of uj. Well, by assumption, fj of uj is less than or equal to fj of delta j somewhere. Z can be either in this part or z can be here. I'm just looking at the first case. So in that case, the constraint pair dx vj less than or equal to fj inverse z, that comes from the upper one, and dx vj less than or equal to uj is equivalent to the smaller of these upper bounds, which is the minimum of fj inverse of z and uj. Okay, whatever the minimizing one happens to be. Now, the case fj uj less than or equal to z which is less than or equal to fj delta j, that amounts to what? Again, it amounts to this. in the first case, what is the minimum here? And in the second case, what is the minimum? Anybody seeing that? If Z is less than or equal to...
In the first case, Fj inverse Z is
Yeah, because this is equivalent to Fj inverse being of Z being less than or equal to Fj inverse of Fj of Uj, so it's equivalent to this. In that case, Fj inverse Z is at, well, less than or equal to Uj, so the smaller one is Fj inverse of Z in this case. That's for sure, okay? In the second case, Z is greater or equal this, which means the minimum is obtained by Uj. And what happens if my Z is greater or equal Fj of, well, not greater or equal, but greater, strictly greater than Fj delta J? Over here, of course, I've got that possibility. There's no upper bound on Z. So for feasible solutions, that's a possibility. How am I supposed to deal with that?
Comes redundant.
Why?
Because the worst you can do with this vertex is Fj of delta J. And if you have Z is larger than that, you will certainly...
I see. If Z is actually over here somewhere, right, then your worst loss for this vertex will be at most Fj delta J, and Z will surely be greater or equal to that. So in an attempt to minimize that, that will be either redundant if the minimum happens to be in this range, or the minimum will be in this lower range, in which case that will not cause a problem. Okay, yeah. Pelin, did that make sense? You seem to be thinking hard. Not yet? Well, in this case, if Z is greater than Fj delta J, I know that the closest distance of Vj to the vertex, to the point set X, it will certainly, this distance inside will be certainly less or equal delta J, okay? Because delta J is the farthest you can go away from delta J. And because of the monotonicity, of course, this being less or equal delta J means Fj of that being less or equal to that. But that is strictly less than Z by assumption. So this constraint is what? Redundant. Because your loss can never be equal to Z in that case, okay? If Z is less than or equal to Fj delta J in the optimality case, in that case, of course, then you go back to the discussion we had here, okay? We're in that domain. Okay. What's the domain of Ej? No, fj of 0. The way I defined it, it's this way. However, I want to remove the restriction on z, meaning that IE require only z being greater or equal fj of 0 with no upper bound on z. In that case, because of the redundancy of that situation, domain of Ej becomes fj of 0 and infinity. Okay? Okay, this is well justified by observing the following. If you look at the constraints, fj of dx vj less than or equal to z, and fj of dx vj being less than or equal to fj of uj, now here z is any feasible solution, well, any feasible value for the original problem. So fj dx vj will be less than or equal to z. Okay. We also had dx vj less than or equal to uj. And because uj is in the domain of definition of fj, is it or is it not? It is. It is. So for that reason, I can apply fj to both sides. Okay. Because of the monotonicity, dx vj less than or equal to uj is equivalent to fj dx vj being less than or equal to fj of uj. Now that is equivalent to, as a pair, fj of dx vj being less or equal the smaller of these upper bounds. Okay? Which is equivalent to, now the smaller of z and fj uj is always in the domain of definition of fj inverse. Does everybody agree with that? This number is always in the domain of fj inverse. What's the domain of fj inverse? fj0, fj delta j. Why is this true? Or is it? Well, if z is less than or equal to fj uj, fj uj is certainly smaller than fj delta j. Okay? Also, fj uj is greater than fj0 because uj is a positive number or 0 at most. Okay? uj could be 0 actually. Okay? All right, so I know that fj uj is certainly less than or equal to fj of delta j. And also it's greater or equal fj of 0. This is because uj is a non-negative number. Did I say that anywhere? Well, any upper bound on distances better be non-negative. If it's negative, then you don't have a feasible solution. Okay? That's a trivial case. And this part is one of the assumptions, isn't it? uj is less than or equal to delta j. That's why. That's assumption number 1. I got lost in my all of these domain and range business. But so this part is pretty well justified, and z is, well, we're still imposing z to be greater or equal 0. So in that case, the minimum of these things, yeah, maybe we should add that. Observe that this will be in the domain of this for fj, for z greater or equal fj0. Yeah, that's the end of the statement. So as long as that assumption is fulfilled, z will be, well, the minimum here will be not larger than fj uj, so it will be in the domain. So with that, this statement is going to be equivalent to what? We apply the inverse to both sides. So the inverse on the left will give dx vj. The inverse on the right will give that one. So the only restriction I need to make to take care of the pair of constraints is this one. And when you impose that for each j, of course, that's equivalent to having z being restricted to greater or equal alpha. Okay? Okay. So we established the equivalence of the original problem with this one, and that one is just an upper bound on the closest distance. So it allows you to actually use the covering algorithm for solving the related cover problem. Okay? That's your R over Wi rather than the old one. Okay? For a fixed value of z. So what you want to do is you want to pick a fixed value for z, and then forget the cardinality constraint here and try to minimize the number of points you want to put so that all the upper bounds are realized, satisfied. Now, I can talk about that for 1 hour, but the time is over, so I'll let you go.